Welcome back. And I'm sure you all know that we're going to have a quiz today. It's going to be towards the end of the lecture. I'll make sure that you have enough time on it. It's going to have full problems. I'm thinking about 20 to 25 minutes. And if you have extended time and you already emailed me, well, you already sent me the accommodation letter. I received it already. I think only one student here. I'm just going to give you more time for you to work on it, and after that you can just upload it. All right, any questions about studying for the quiz? Like I said, the material we talked about last time on quadratic functions and the polynomial functions, that's not going to be on the quiz. It's just the material we talked about the first week. All right, any questions? Well, you can also think about it now if you need a little bit more time, and maybe before we take the quiz, we can spend some time going over some final questions.
Actually, I was wondering, is there like a good resource that you'd recommend for like, I know when I went and looked at the homework, for example, and tried looking at some of the problems that I had messed up, it only gave like one separate problem to practice with. Do you have like any recommendations for a resource for like more practice problems or something?
Yeah, so the textbook, right? The textbook we use, the problems that on the website, they are the same problems coming from the textbook. But if you go to the textbook, the online textbook, and at the end of each section, you probably will be able to find a lot more problems. If you just click on the tab, go to the specific section, and then at the bottom of each section there are a lot of practice problems called homework. But also throughout the section on the web page, you know, that they have examples, and they say like try it. So they give you another example similar to the example that they go over.
Okay, I'll keep that in mind.
Yeah, and I think that'll be somewhat good to look for practice problems. They also have chapter review problems. Yeah, good question. Any other questions? Sorry, Tim, looks like you tried to say something, but I didn't hear what you said.
Can you hear me now?
Oh yeah, yep.
So is it okay if we use like an iPad and do notes, and then if we need to submit anything, submit a PDF like that?
Absolutely. That's a good point, and I actually put in the instruction for the quiz. Yes. So if you know, like me, I write on my tablet all the time, right? So if you feel comfortable writing with iPad, and at the end, you just have to save it as a PDF and upload it. Actually, that's probably easier. But if you write on paper all the time, just make sure you scan every page, like all the pages as a one PDF file, and upload that. So it has to be one PDF file. But that's a good point, Tim. Thank you.
I just didn't know if you wanted like all on paper, or if you were okay with that.
I'm okay with it, but I would just add that, like, I mean, I trust everyone, right? This is going to be, well, you're going to take the quiz, and I'm not there to watch you, and I don't think you need to be watched because, at this time, we are all adults basically, and I trust that, you will follow the instructions. Do not use textbooks. Do not use notes. Do not use calculators. I don't think the problems are difficult. I don't think calculators is required. So all the numbers should be, relatively easy to calculate if you do need to calculate anything. Don't look up the problems on the internet because it's very easy, and sometimes you can just, there's a lot of resources that actually solve the problem for you, but don't do that. This is the opportunity for everyone to kind of just to figure out whether they know the material. Just think about this as something to check your understanding, basically. It's not, I mean, obviously the grades matters, right, at the end. And I want you to all pass this class, but I just don't think it's in your benefit if anyone is like, find the answers from other resources other than their own work. Good point. All right, any other questions about the quiz? All right, here's a chat message. The quiz is today, correct. So the quiz is going to be towards the end of the lecture today. All right, any other questions? All right, if you don't have questions, so my plan is that I'm going to go over some of the new materials. And again, what I'm going to talk about now is not going to be on the quiz. And then the quiz is at the end, make it easy. All right, so let me begin with polynomial functions that we talked about last time. So suppose, so here's a couple examples. Suppose we given that f of x equals x to the 6 minus 3x to the 4th plus 2x squared. And what we're going to do is we're going to find the zeros and state the multiplicity of each zero. Now, the same question could be saying, okay, find the x-intercepts, right? Or could be finding the roots. It's the same process to find the zeros. What we do is we're just going to set y equals 0. Or same thing when we're finding x-intercept. So we're going to set f of x equals 0. And we're going to solve for x. So 0 equals x to the 6 minus 3x to the 4th plus 2x squared. Now we have three terms. The first thing we want to do, we want to factor. So let's factor out x squared from all terms. And then we are left with, if we take out x squared from x to the 6, we have x to the 4th. Then if we take it from 3x to the 4th, we get negative 3x squared. And if we factor out x squared from 2x squared, we get 2. Right, so that's equal to 0. This is a good thing because we have a product equals 0, which means one of them is 0 or both of them could equal to 0. But the question is, can we factor further, right? And it turns out that in the second part, if we think about, let's see, here we have an x squared, then we have x to the 4th. So if we think about x to the 4th as x squared squared, so we're going to end up with x squared. I'm going to use brackets here. So I get x squared squared minus 3x squared plus 2. So we can actually think about this as a quadratic expression that we can factor further, but keep in mind that x squared is kind of like the x in a quadratic expression. So if we try to factor the bracket part, we should end up with two terms that multiplied. And because we have x squared squared, so each of them will have x squared to begin with. Just like we factored before with, like, for example, x squared minus 3x plus 2. We can factor this into a product of two factors. Same thing here, but we just, instead of having x to begin with in each parentheses, now we have x squared. And we want two integers that when we multiply give us 2, but when we add, we get negative 3. So the two integers will be, when we multiply them, give us 2. So that's going to be either 1 times 2 or negative 1 times negative 2, one of them. But when we add them, we want to have negative 3. So the two integers is going to be negative 1 and a negative 2. Right. So from here, we can continue to factor because we have x squared minus 1, that's minus 1 squared. We can use the difference of square formula. So that's x squared times x plus 1 times x minus 1. And the x squared minus 2, you can either leave it or you can factor that in terms of x plus square root of 2, x minus square root of 2. It doesn't matter. I can just leave it for now if we don't see that as difference of squares. And remember, this is equal to 0, which means every single factor in this expression is going to equal to 0 because the product equals 0. So x squared could equal to 0. X plus 1 could also equal to 0. X minus 1 could be 0. And the x squared minus 2 again could be 0. Any of this could be 0, or all of them could be 0, or any combination of each of these equations could be true. So from here, we can solve for x. So from the first one, we get x equals 0, but that's x squared give us 0, so x equals 0 is actually having a multiplicity of 2. Because of the square. X plus 1 equals 0, that gives us x equals -1. And then we have x equals plus 1. And x squared minus 2 equals 0 gives us x squared equals 2. So if we take a square root on both sides, since we're solving for x, we have to add plus minus. So we get x equals plus minus square root of 2. So those are the x equals -1 that has the multiplicity of 1. And the x equals +1 also has a multiplicity of 1. X equals plus minus square root of 2 again have a multiplicity of 1. So this function, this example I gave you, has 5 x-intercepts, or 5 zeros, if we think in that way. Now, if we count repeated zeros as separate zeros, we actually have 6 zeros. All right, any questions? So if repeated zeros counted twice, I mean like the zeros with multiplicity of 2, if that counted as twice, then the function f of x equals x to the 6th power minus 3x to the 4th power plus 2x squared has 6 zeros. Even though we have like 5 different ones, but because x equals 0 repeats itself. So if we count that as 2 zeros, we actually get 6 zeros. There's a fundamental theorem of algebra, which says so fundamental theorem of algebra, which says if f of x is a polynomial with a degree n, n greater than 0, and then f of x has n zeros if multiplicity is allowed. What that means is that if we count multiplicity of 2 as the 2 zeros, right? If 0 has multiplicity of 2, we count that as 2 zeros. Then for a polynomial function with degree n, then that function is going to have n zeros or n roots. It does not mean it's going to have n x-intercepts, because x-intercepts are strictly real numbers. Right? So let me go through any questions on this example.
Can you explain how you got 6 again?
Yeah, good question. So when we solve the zeros, so we have x squared equals 0, so that gives us x equals 0, right? But because we had x squared there, so we really had, if we follow the algebra, we take square root, so we get x equals plus minus square root of 0, which is plus minus 0. So that really, the x equals 0 really is like a 2 zeros. like two roots, but they are the same. So we write x equals 0 with multiplicity of 2. And with x plus 1, when we set equal to 0, we get -1. X minus 1 give us x equals +1. And x squared minus 2, when we solve that equation, we get x equals plus minus square root of 2. So that's two different zeros. So that's x equals square root of 2, x equals negative square root of 2, right? So if we add up all the zeros, we have x equals 0 twice, so that's 2, and x equals 1, so this 2 from here, 1 from here, 1 from here, 1 from here, 1 from here. So we get 6 zeros.
Okay, so then why doesn't x plus minus square root of 2 have a multiplicity of 2 then?
That doesn't, because it's a two different value for x. So even though we have x squared equals 2, but when we solve that equation, we get two different numbers. We get x equals square root of 2 and x equals negative square root of 2. They're not the same value. They're two different values. But
Okay.
with the case of x squared equals 0, it doesn't matter whether we have positive 0 or negative 0, right? We just write as 0. It's the same
Okay.
value repeats itself.
So is it just with 0 then?
With zeros, or if we had, let's see, if we have example, at some point we have this expression, so we got 0 equals, let's say x minus 1 squared times x plus 2 or something continues, right? So if we have this expression and we set the first one equals 0, so we get x minus 1 squared equals 0, then we can take a square root on both sides. So x minus 1 equals plus minus square root of 0. And we get x equals plus minus square root of 0, which is 0 plus 1. So we really just end up with 1, just one value, even though we should have 2. But it's the value 1 itself repeating itself here. So here, this 1 also have a multiplicity of 2. It's because of this square. The exponent of x minus 1 is 2. So that's why we have a multiplicity of 2. We're not going to end up with different values. We have the same value repeating. So a general rule is that if a function, so let me write somewhere below here. So if f of x in the factor form, so if f of x equals x minus h to the p, and maybe there's some other terms after this, this is the factored form of f of x. Now, when we set this equal to 0, we get 0 equals x minus h to the p, and then a lot of terms coming after that, which means this part could possibly equal to 0. So we get x minus h to the p equals 0. When we take p's root, so we get x minus h, but because we have x minus h to the p's power, when we take the p's root, we should have, just like we take a square root, we have plus minus. If we have a cube root, we should have 3 numbers. But when we take the p's root of 0, we in theory should have p different values we can get. But that's just going to be 0. There's only one number when we take p's root of 0. So we add h to get x equals h. So we get this number h as the only 0 here. But it repeats itself p times because of the exponent we had with this term. So this 0 has multiplicity of p. If p equals 3, so it has a multiplicity of 3. If p equals 5, it has a multiplicity of 5.
Okay, that makes more sense. I was just confused as to why one had like a square and the other had a square, but then why it was only 1 and 2 for the multiplicities.
Right, right. Good. Good question. Any other questions about this problem, or just in general about the multiplicity of a 0 or of a root? All right, the next example I have, if you don't have any questions, is, let's see, f of x equals x cubed minus 5x squared minus x plus 5. Again, we're going to find the zeros. So if we want to find the zeros of this example, we're probably going to try to factor because that's probably the technique that we know. Well, you might know other techniques, right? That's fine. But let's suppose we don't know any other techniques except for factoring. So we're going to try to factor this. There are 4 terms, and we begin with the x cubed term. So what we do is we're going to just factor the first 2 terms. We're going to look at the first 2 terms, take out anything we can. Then we're going to look at the last 2 terms and try to factor anything that's possible, including a -1. Sometimes it helps. So here, if we factor f of x, the first 2 terms will give us x squared. And if we take out x squared from x cubed, I get x remaining. If I take out a x squared from 5x squared, I get -5 remaining. Okay, then you probably think, okay, there's nothing common. We can take out -x plus 5, right? But the trick here is we want to end up with some expression that looks like x minus 5 because we want to be able to factor again. So what I'm going to do is I'm going to factor out a -1 from the last 2 terms. So take out the negative. If I take out the negative from -x, I get x remaining. But if I take out a negative from +5, I get -5. As you can see now, I get x minus 5 as a factor in the first part. Then I have x minus 5 as a factor in the second part. So they're the same. Because we have this factor x minus 5, if we treat x minus 5 as, as a chunk, just think about that's the one entity that's being multiplied by x squared, and then it's being multiplied by -1. Right? If you think about x minus 5, it's kind of like x or x squared, right? It's the one entity. And we can factor this out to the front. So we can factor out x minus 5. And if I take out x minus 5 from x squared times x minus 5, so I get whatever is remaining, right? X squared. And if I take out x minus 5 as a factor from 1 times x minus 5, so I get -1 remaining. So we factor twice. The first, we factor the terms separately, the first 2 and then the last 2. And then we're going to try to factor again. In this case, when we factor the second time. So what we factored is a expression with a subtraction. So it's not just like x or x squared or x to the 4th power. It's a subtraction, but we have to treat that subtraction as something, it's one part, it's one chunk that we can pull out of both terms. All right, give me a second because my headphones is about to die. Let me plug in the chart.
Your mic's not working. Oops. All right, sorry, give me a minute. I think there's connection issues with my headphones. It's all good. Your mic was working when you said that. So.
Okay, sorry about that. It looks like, okay, I think we're good now. If there's trouble hearing me, please let me know. So we can factor this further. So that's going to be x minus 5. We leave it, but x squared minus 1 squared. Well, just to remind you, I think I assume that you know this. So if we have a squared minus b squared difference of two squares. So that's going to be a plus b and a minus b. So here we can factor, so the x is equivalent to a, 1 is equivalent to b. So that's going to be x plus 1, x minus 1. So now we completely factor every term there. So we can set this equal to 0 equals x minus 5, x plus 1, x minus 1, and then we can solve for x by setting every factor in this part equal to 0. So x minus 5 could be 0, x plus 1 could be 0, x minus 1 could be 0. So we have x equals 5, x equals -1, x equals +1. As you can see that every factor has a power of, has a exponent of 1. So the multiplicity of those zeros are just 1. All right, any questions about this example? I wanted to go over this because it's really just factoring.
I might have missed a piece. When did -1 get squared?
The -1 get a square. That's a good point. So I didn't have that -1 square, right? I just had a -1. What I did is I want to show that the x squared minus 1 is really the difference of two squares, because if we have 1 and if we have 1 squared, they're the same, right? They're equal. They're not the same, but 1 square equals 1. So every time we see 1, we can always add a square if we need it to make a difference of squares.
I see now. Thank you.
Yep. I also want to show that earlier in the previous problem, I set the function equals 0 in the beginning, but here I factored the function first and then set it equal to 0. It really doesn't matter when we're going to set it equal to 0 if we try to find the zeros. You can try to factor first and then set it equal to 0, or do it the other way around. All right, good questions. Okay. All right, so the next thing what we're going to do is we're going to take this example I have. So the example is let's see, g of x equals x minus 2 squared, 2x plus 3. I'm going to add a negative in front of this. So what we're going to do with this function is that we're going to go through the list of a few things, and at the end, we're going to graph it. So at first, we want to find the x-intercept and y-intercept. Well, x-intercepts could be multiple, y-intercept. When we find the x-intercept, we also probably want to find out the multiplicity of those x-intercepts, because that will give the local behavior of all those x-intercepts. So y-intercept, and then we're going to find the leading term. So LT means leading term, and then we obviously need to find the degree of this function for practice, and we're going to find end behavior of this function, behaviors. So as x goes to infinity, we want to know how the function behaves. As x goes to negative infinity, we want to know how it behaves. And then we're going to graph it. All right, so let's just do it one at a time. So to find the x-intercept, again, I'm just going to set the function equals 0. It's already factored, so I don't have to do too much. So I get 0 equals the negative x minus 2 squared, 2x plus 3. Actually, a second thought, I might change the question. Let's see, I'm going to change the question slightly to reflect a common mistake students make. So let's see, instead of having negative, I'm going to make it negative, let's see, -1/2 as a coefficient at the front. I want to show you this because that's a common mistake when we find the x-intercepts. For example, here, so we have 0 equals -1/2 times x minus 2 squared times 2x plus 3. So a mistake I noticed in the past from students is that they will think, oh, -1/2 must be one of the 0 because we get -1/2, we have to set equal to 0. No, so this is not, this is just a constant. -1/2 is a constant. It doesn't give us a 0 or x-intercept. Be careful with that. Only the parts with x will give us x-intercepts. So x minus 2 squared could equal to 0. 2x plus 3 could equal to 0. You don't even need the parentheses here. So from the first equation, I'm going to have, by taking square roots on both sides, add plus minus, but I still have x minus 2 equals 0, which give me x equals 2. Now, because I had x minus 2 squared to begin with, before I take the square roots on both sides, so that means the square there tell me that the x equals 2 has the multiplicity of 2. And the 2x plus 3, so that's going to give me 2x equals -3 and the x equals -3/2, which has a multiplicity of 1. And now we're going to find the y-intercepts. To find the y-intercept, we simply make x equals 0. So to find y-intercept, we're going to set x equals 0. So we get g of 0 equals -1/2, 0 minus 2 squared, 2 times 0 plus 3. So if we carry out the algebra here, so we get -1/2 times -2 squared. Be careful, -2 square that. Square of -2 is +4. It's not negative, so that's a +4. And then 2 times 0 is 0. 0 plus 3 is 3. So it turns out we're going to end up with, let's see, 1/2 times 4, that's a 2. So we get -2 times 3, -6. That's a -6. And to find the leading term, and if you remember in the previous lectures, there's one example when we find the leading term, what we do is we're just going to take all the coefficients, all the x parts, we're going to multiply them together along with the exponents the x have, all the x parts has. So to find leading term, so that's going to be, so all the coefficients, including any coefficients in front of all the factors. So we got -1/2, that's a coefficient, times the first x part is x in the first parentheses with a square. And then the next x part we have is x, but there's a coefficient 2 in front of it, so 2x. So if we multiply all of those together, we get the leading term. So that's going to be -1/2 under the 2, multiply together, give me 1. So then we have x squared times x is x cubed, so we get -x cubed. That's my leading term. And from this leading term, I can tell what the degree of the polynomial function is. The degree is going to be the exponent of the leading term, which is just going to be 3. And from the leading term, I can figure out the end behaviors. So we have a -x cubed. If you're familiar with the graph of -x cubed, so the graph is going to go to the infinity on the left and then go to -infinity on the right. So the two ends pointing to the opposite direction, with the left side going up, the right side going down. So that's the end behavior. For -x cubed, it's also the same for this polynomial function. And with that said, now we can actually try to graph it. To graph polynomial functions, we're just going to graph the x-intercepts, the y-intercepts, the end behaviors, and make sure everything's correct. So let's see. For x-intercepts, I have 2 with a multiplicity of 2 and a -3½ with a multiplicity of 1. So let's see, this is a -1, -2. So let's see, this is a -3½ with a multiplicity of 1. So that means the graph is going to cross this x-intercept like a straight line, either going to be like this or like this. We don't know which way it is. But let's just say it looks like that for now. And x equals 2. So this is 1, 2. This is also an x-intercept, but it has a multiplicity of 2. So it's going to be a U-shaped at this x-intercept. So it's going to be like this, or maybe it's upside down like this. It depends how the graph is going to approach this x-intercept, from above or from below. All right, so I'm just going to leave it like this for now. But it doesn't matter, we can figure out later. Just remember it's going to be a U-shaped here. All right, Y-intercept, we found out that's going to be -6. So -2, -4, -6. So that's going to be here. And the end behavior is left side is going to go up, right side is going to go down. So it looks like this. And now we just have to try to connect the points under the arrows. So what I do is I always begin with the tail of the arrow on the left. So if I trace the tail here and I try to go right, so at first it must go through this first x-intercept at -3½ Well, if it approach it from above, there's no other way, it must coming down like this. And then as it goes down, it has to eventually cross the y-intercept, and it just like that. There's no other way to cross a y-intercept. And after it crosses the y-intercept, it keeps moving. I mean, it could go up a little bit, or it could go down a little bit more, but eventually it has to go to the second x-intercept at x equals 2. So at some point it might turn around and then go to this x-intercept. Remember that it must touches it and then bounce off. So it's a U-shaped or upside down U. So it's not going to be above, it's actually upside down U. Looks like this. And then it's going to connect to the tail of the second arrow. I usually just erase this arrow and just draw an arrow there. Any questions about graphing? To be honest, when I study polynomial functions, this is probably the most interesting part, because you kind of have like a different information, and then you just try to connect them, make sure that make sure the curve is smooth and it doesn't have any contradictions with intercepts or the end behavior. All right. If you don't have any questions, one thing we could do is we can look at a few concepts sort of on its own in this section. Yeah. Okay. All right, let me ask you, should we graph another polynomial function for practice? All right, is anyone want me to graph another example? I'll do that for you, and but if no one wants to do it, that's fine. All right, looks like I'm not hearing from anyone. Okay, then, well, in that case, let's move on. So the next thing I want to talk about is it's just kind of like a topic, doesn't quite fit in with the polynomial functions, but it is there in the section. It's called even and odd functions. So I'm going to give you the sort of like the criteria or the condition for even and odd functions first, and then I'm going to go through maybe two examples. So a function f of x is even. To test whether it's even or not, we can look at f of negative x. So if a function f of x is even, f of negative x must equal to f of x. So the graph looks like this. Suppose we have some function, let's see, it looks like perhaps like, I don't want to use that function. Perhaps it looks like this. And on the left side, it's going to have a sort of a symmetric shape. So this is x equals 0, the y-axis. And over here, let's see, this is x, some x value, and it has a y value here. That's a f of x. But then if I pick a point on the left, that has the same distance from the y-axis. So this will be negative x. And this will be f of negative x. As you can see, if the function is perfectly symmetric over y-axis, then f of x and f of negative x, they must meet with the same y value. So they must have this, they must be equal. So that's what this sort of condition is for f of x to be even. And then for a function to be odd, so f of x is odd, then we can say f of negative x must equal to negative f of x. So if we think about graphs, let's see, I just like this. And then this side must look like this. So suppose this is my x value, and this corresponding y is f of x. On the left side of this origin, y-axis, I have, let's see, this is my x. I'm not drawing it correctly, I think. But anyway, you get the clue. So if this is my negative x, this will be my f of negative x. As you can see, if the graph is perfectly symmetric over the origin, then f of negative x, it has a negative value, but it has the same magnitude as f of x, just on the opposite side of the y-axis. So that's why we have this f of negative x equals negative f of x. And this, so that's even in our function. So you can also think about graphically even functions are symmetric over y-axis. And the odd functions are symmetric over the origin. Basically have the 180 degrees rotational symmetry about the origin. So here's an example. Let's see, I'm going to give you, let's see, f of x equals x squared plus let's see, plus 4 is f of x in even or odd or neither. So if f is f of x even function, or maybe an odd function, or neither even or odd. All right, so the quick way to test it is using the conditions that I boxed. So we already have f of x. What we're going to do is we're just going to find f of negative x and compare the result with f of x. So let's see, find f of negative x. So that's going to be negative x squared. If we take negative x, put into f of x, plus 4. And if we simplify this expression, we get negative x squared, which is the same thing as x squared, plus 4 is just plus 4. It doesn't change. So we end up with x squared plus 4. So that's f of negative x. But is that the same as f of x? And the answer is yes. So same as f of x. So we have f of negative x equals f of x. And if that's true, then f of x is even. Any questions on this example? And here's the second example. What about f of x equals x cubed plus 4x? Right, yeah, we can stop there. So f of x equals x cubed plus 4x. Is this function even or odd, or neither? We're going to do the same thing. We're going to find f of negative x by taking negative x put into this f of x function. So we get negative x cubed plus 4 times negative x. And we're going to simplify every term. So negative x cubed, if you remember, that's just negative x cubed. And then 4 times negative x, that's a minus 4x. So that's the expression for f of negative x. And we can compare this with a given function, f of x. Are they the same? No, right? Because both terms become negative. So not the same. So that means this is not even. So f of x is not even. Well, is this an odd function? Well, let's find out. So let's see. What about negative f of x? Because that's what we need to compare f of negative x with, right? If f of negative x equals negative f of x, then it's odd. So let's see. So negative f of x equals negative x cubed plus 4x. That's going to be negative x cubed minus 4x. And it turns out that negative f of x and f of negative x, they are actually the same. So that means f of x is odd. And it turns out that functions like 4x, like x cubed, so those individual pieces of the function f of x, they are odd. So if we take an odd function, add to another odd function, you end up with an odd function. And another example, I'm not going to do it fully, but I want to kind of show you. So if we have f of x equals, let's see, x cubed plus x squared plus 4x minus 4, or plus 4, doesn't matter. So if we have some function like this, is this going to be even or odd? Well, the truth is, because this one is odd, this one is even, this one is also odd, this one is even. When you have an odd and an even function mixed together in terms of an addition and a subtraction, it's going to be neither. But with the previous example, x cubed is odd, 4x is also an odd function. So if you take an odd function plus another odd function, you get an odd function. The first example I gave you, x squared is even. 4 is also even because that's like a 4 times x to the 0. So that's an even. So if you have two even functions, you add them together, you still end up with even function. All right, so that's odd and even functions. And the next thing we have here is, let's just look at my notes, make sure everything's fine. Okay. So the next thing I have is called intermediate value theorem, which is again just a topic sort of on its own here. Intermediate value theorem. I'm just going to go through it quickly. That's only one example on this on the homework. So let f of x be a polynomial function if f of a and f of b has opposite signs, means one is positive, one is negative. For example, let's just choose f of a is less than 0, f of b is greater than 0. So they have opposite signs. Then there is at least hold on, I gotta fix something on my computer. So there is at least one C value. So C is the X value such that, so ST, if you haven't seen this before, it means such that f of C equals 0, which means when X equals C, f of X equals 0. So when X equals C, f of X equals 0. So what this says, I know it's like, if you don't see the theorems a lot in the past, what that means is that suppose we have some function, polynomial function, and for X equals A, let's say the function is negative. So this is the A, this is the f of A, which is negative. And then somewhere you have B, let's just say B is here, doesn't matter. So B is here, and the f of B is positive, so they have opposite sign, which means somewhere between A and B, there's at least one C, could be multiple, such that f of C equals 0. So this is where the C is. What that means is that the function must cross the x-axis at least once. That's another way to think about it. So there must be at least one x-intercept between A and B. So let's use this in an example. So here we are given, this is the example I have is, so f of X equals X minus 2 squared minus 1. Show that f of X has at least one C, one x-intercept. Let me rewrite it. At least one x-intercept, or 0, or root between x equals 2 and x equals 5. So we just need to show, we don't need to find out what it is, but we just need to show the function has at least one x-intercept that's between 2 and 5. So we're going to use the theorem here. The way to show it, we're not finding it, we just want to show. The way we show it is that we're just going to take x equals 2, we're going to put it into the function. So for x equals 2, f of 2, put 2 in the function, so we get 2 minus 2 squared minus 1. So that's going to be 0 minus 1, which is negative 1. So that's going to be less than 0. And then for x equals 5, and again, I'm going to put 5 into the function. So we got f of 5 equals 5 minus 2 squared minus 1. 5 minus 2 is 3. 3 squared is 9. Minus 1 equals 8, which is positive. So by finding the corresponding y values for x equals 2 and x equals 5, we found out that there's one, so whatever the function looked like, suppose we don't even know what it looks like. We know that when x equals 2, it's going to give us a negative y value. And for x equals 5, it's going to give us a positive y value, 8. What that means is that because the function is polynomial, so there must be somewhere between those 2 points that the function is going to cross the x-axis. Means there must be one, at least one x value such that f of x equals 0, or c such that f of c equals 0. So there must be at least one x-intercept. So we don't even have to do anything else. We can just say, since f of 2 less than 0 and f of 5 greater than 0, they have opposite signs. And according to the intermediate value theorem, so based on intermediate value theorem, there exists sometimes, just so you know, later on, when you take calculus, you're going to see this notation. If the abbreviation for there exists, it's a E, but backwards E. So if you write E backwards, so that means there exists at least one x-intercept or zeros, 1 0 between x equals 2 and x equals 5. So that's all we have to do for this example. We don't need to find out the actual x-intercept. We just want to show if we know two x values, one give us a positive y, one give us a negative y, then we know somewhere in the middle there must be a x-intercept corresponding to y equals 0. All right, any questions on this? The last thing I want to do here is, so the last thing I want to do in this section is to talk about a couple of terms. It's called global maximum minimum. It's sometimes called absolute maximum minimum. So when you see them, you think about them, they have the same meaning, versus local maximum or minimum, and sometimes this is called a relative maximum minimum. So I'm not going to go through the definition because they're fairly straightforward. Global means everywhere on the graph, just like absolute means absolutely the maximum, right? Local and the relative just means in the small parts of the graph, it's a maximum. So I'm going to use graphs to make it easy. So let's suppose we have a graph that looks like, let's see, oops, something like this. And I want to do something different here. So let's see, this is my graph, and this is my XY axis, right? So if we look at this graph, it's going to continue in both directions. And if we look at it, this point, that's the minimum, at least in this area, in this region. So we can say, okay, that's a minimum. And this point next to it, that's also a minimum. Oh, sorry, that's a maximum, at least for that region. And this point, that's a minimum for this part. And it looks like if I draw it correctly, so it looks like that part in this small area, that's also a maximum. And maybe this point here, that's corresponding to minimum. So if we look at this graph, they get multiple points that corresponding to minimum and a maximum. But all of those are called local or relative minimum maximum, because in that local region, they are minimums and the maximums. But if we look at the entire graph, which one is a maximum, which one is a minimum, right? And if it turns out that if we look at the entire graph, because the both arrows going upwards means they continue to increase, so there's no global maximum, because it goes to infinity and infinity doesn't exist. It's not defined. So this function has no global or absolute maximum, because it goes to infinity and we don't know how big is infinity. But does it have a global minimum? Well, then we're just going to look for which one of the local minimum is really the smallest. And it turns out the first one on the left looks like it's the lowest y value if we compare all the minimums. So the function has a global minimum. And obviously it has multiple 3 local minimums and 2 local maximums as well. Okay, so that's how we identify the minimum and the maximum for global min and the max, also for local min and the max. And another thing I want to point out that about those points that give us a local minimum and maximum. So those are called turning points. So each of this point here, whether it's corresponding to a local minimum or a local maximum, so those points are called turning points, because this point is corresponding to where the graph changes direction. For example, if we look at this local maximum here, so on the left side, the function increases, and then when it reaches to this local maximum, it turns around to decreasing. So the function from going up, turning around to be going down. So that's the turning point. Same thing with the local minimum. So the function decreases going downwards, and then it changes direction by going upwards. So turning points are where function changes direction. So turning points where function f of x changes direction. All right, so those are just terminology here. Any questions on those terms? A typical question probably would be, okay, here's a graph of this polynomial function. Identify the global maximum or global minimum. But you're probably given a graph, so you don't have to worry about it. It's we don't try to find the global minimum maximum directly from the function. For this class we rely on graphs to do that. And if you take 425 calculus 1, you're going to learn how to actually find the global minimum or maximum or local minimum and a maximum by taking the derivative and then finding the critical points. In this case, it's equivalent to turning points. Any questions? All right, if you don't have questions, let's take a break. It's already 7:14, so let's take a break. So let's be back here by 7:20. So let's take a break. So back by 7:20. And if you have any questions, feel free to ask me. I'm here.
When do you think we'll take the quiz?
I'm thinking, so 7:20, so I'm probably going to talk for another 20 minutes. No, 7:20, 40, 50, about another half an hour, and then we can take the quiz. So maybe around 7:50.
Sounds good.
Yep.
Perfect. Instructor.
Yep. Is it Tim?
Yep.
Okay.
Did you happen to get my email?
You sent it a couple of days ago, right? Not today.
No, the one I just sent today.
You just sent it today. Okay. Hold on. Let me stop sharing. Actually, let me stop recording first. All right, welcome back. Let's get going. So like I said, I'm going to talk for about another half an hour, and then we can probably get situated with for the quiz. All right, so the next thing I'm going to talk about is polynomial division. So this is in section 3.5, polynomial division. So it might sound like it's a sort of a isolated topic. It is for now, but it's actually useful for the next couple of sections when we try to find all the zeros for some polynomial function or for some polynomial equation that we couldn't do by factoring. So what we want here, so suppose, so let me just begin with the example. So let's see, we have polynomial expression, which is 2x cubed minus 3x squared plus 4x plus 5. And I want to take this expression, I want to divide it by x plus 2. Right. So another way to write it using long division notation, and that's exactly what we're going to do here. So we have 2x cubed minus 3x squared plus 4x plus 5. I'm going to divide it by x plus 2. So we want to know what is the quotient, what is the remainder if there's any. Now, I don't know how comfortable you are with long division, with polynomials. For me, I didn't learn this until I was in college. I just never had the opportunity to study it in high school. Some of you probably feel the same. So before I do this, I want to quickly use a simple example with long division with numbers. So the example I have is, let's just see, we take 178, divide by 15. And if you remember that the first thing we do, we want to get rid of as many digits as possible in the beginning, right? We can get rid of the hundredth digit by multiply by 10. So 10 times 15, that's 150. We can get rid of the 1 in the 178. So we're going to multiply by 10. So that's a 1 in the 10th digit. So we put directly above the 7. So I get 1 times 1 is 1, 1 times 5 is 5. And then what I do is, instead of adding them, I'm subtracting 15 from 17. So that's a subtraction. So it's always subtract. So 1 minus 1 is 0, 7 minus 5 is 2. Right, so we get 2 from the first 2 digits. And then what I'm going to do is I'm going to bring down the 8. And now I need to get rid of this 2 I have in the 28. So I know I have 15, but if I take 15 multiplied by 1, I get 15. If I multiply by 2, I get 30. 30 is too big, so I'm going to multiply by 1. So 1 times 15 is 15. And again, I'm going to subtract. So in the process here, it's always subtraction. Make sure you keep that in mind. It's always subtracting. So we got 2 minus 1 is 1. 8 minus 5 is 3. So we get 13, which is smaller than the divisor 15. So that's a remainder. And we're not using any decimals in this case. So, and this part is the quotient. And at the end, we can write 178 divided by 15 is equal to 11 plus the remainder 13. We can write as 13 over 15. That's one way to write it. You probably don't use this notation a lot, but that's a correct notation. All right, so I just want to use this example to show you when we take polynomials and perform long division, it's the same process. Always subtract until we cannot subtract. So let me go to this example on the left with the polynomials. So the first thing I'm going to do is I'm going to divide by x plus 2, but I begin with 2x cubed. So I want to get rid of this term first. So what do I multiply x plus 2 with? That will give me 2x cubed. Well, I already have an x, so that means if I take x multiplied by 2x squared, I could get rid of 2x cubed. So that's what I'm going to put. I'm going to put 2x squared, but I have to line it up correctly, put it above the x squared term, so 2x squared. So now if I check 2x squared times x, that's 2x cubed. What about the plus 2 times 2x squared? I don't care. So let me just write down the terms. So 2x squared times x. So I get 2x cubed. So I want to put it below the x cubed term. And then 2x squared times 2x times the 2. So that's going to be positive 4x squared. So plus 4x squared. So that's the first part. I'm going to erase those two. And just like with the long division with numbers, we need to subtract. So we need to subtract this from the expression above. So if I take 2x cubed minus 2x cubed, I get 0, x cubed. And be careful, the next part, I have negative 3x squared. Let me highlight this. I get negative 3x squared. I'm subtracting positive 4x squared. So I have negative 3x squared minus 4x squared, right? So that's going to be negative 7x squared. Does that make sense? So it's always subtraction. And now I'm going to bring down the 4x from the next digit, the next term. So plus 4x, bring it down. And then the next thing I want to get rid of in the following step is I want to get rid of this negative 7x squared. So I have to think about, okay, what term multiplied with x will give me negative 7x squared? And then the term will be negative 7x. So if I take negative 7x multiplied by x, I get negative 7x squared. And then if I take negative 7x times positive 2, I get negative 14x. So now what I did is, sorry, I should draw those lines. What I did is I take negative 7x multiplied by x, give me negative 7x squared. Then I take negative 7x multiplied by 2, I get negative 14x. And again, just like before, I need to subtract now. So I'm going to subtract this expression. So again, subtraction. So negative 7x squared minus a negative 7x squared, so it's become a positive 7x squared and a negative 7x squared, so that becomes a 0x squared. But then I have 4x minus, so let me highlight it again. So I get 4x positive minus a negative 14x. So that's where I'm saying you have to be very careful, because a lot of times you end up subtracting a negative. So 4x plus 14x, that's an 18x. And now I'm going to bring down the 5. So the next thing I'm going to get rid of in the following step is this positive 18x. So x times what number give me, or what expression give me 18x? The answer is positive 18. So I'm going to put it directly above the term with the numbers 5. So that's positive 18. So what I'm going to do is I'm going to take 18 multiplied by x. So that's the 18x. And the 18 times 2. So 18 multiplied with 2, that's the 36. So again, I need to subtract. So minus this expression. So let me do it carefully here. So 18x minus 18x. That's a 0x. 5 minus 36x. So that's going to be 5 minus 36, negative 31. So this is my remainder. I know it's my remainder because in the quotient, I already reached the term with no x, the constant term 18. So I'm not going to continue in this long division because I'm already reaching a point that's the end of the polynomial expression. All right, questions?
Is there a specific way you want us to write that out? So like just like R31, negative 31 or something for remainder?
Yeah, absolutely. That's a good point. I was just about to go there. Thank you. So at the end, when we write down the answer, right, we could write, so the question was 2x cubed minus 3x squared plus 4x plus 5. That was the dividend. divided by the divisor x plus 2. So the answer, the way we write it is we're going to write down the quotient, which is what I put in the red box, 2x squared minus 7x plus 18. And then we're going to add the remainder, but the remainder is not just negative 31, it's negative 31 divided by x plus 2. We always take the remainder and put it above the divisor. So we take the remainder and divide the right as the fraction at the end for final answer. So that's one way to write it. Another way to write the sort of the problem here with the answer is that we can also write 2x cubed minus 3x plus 4x plus 5 is equal to the quotient 2x squared minus 7x plus 18 times the divisor x plus 2 plus the remainder negative 31. So either notation is fine. Personally, I prefer the first one. So let me just highlight, I prefer this notation, but it doesn't make a difference if you write it the second way. But as you can see, the left side are different, right? Depends on how you write it. All right, any other questions? Okay, if you don't have questions, let me go through another example here. So the second example I have is we're going to take this polynomial 6x cubed plus 11x squared plus 15, and we're going to divide it by x squared minus 2. Now, before I do anything here, I want to, okay, Tim, do you have any questions? I didn't know. I thought you might have a question.
I actually do have a question. Is the cube and the square always going to be in the same order in this?
It's always going to be in the same. Sorry, I didn't quite catch.
Like the 2x cubed and the negative 3x squared. Is it always going to be in that form first?
Oh
Like
yeah, yeah. Right. Sorry, I forgot negative 3x squared. Doesn't always. Okay. If I understand you correctly, the 2x cubed and the minus 3x squared.
Basically, is it always going to be in this format?
Right, with the exponent decreasing, you meant?
Yes.
Correct. Exactly. So that's actually something we need to do if we given a long division problem. So the first thing we have to make sure that two things. Make sure one, the exponents are decreasing in all those terms. So basically we have to put in the standard polynomial expression. And the two, we have to make sure that if there's any term that's missing, for example, this example I gave you, x cubed, x squared, doesn't have x term, right? Just jump to the 15 constant term. So if any term is missing, we're going to add a 0. So if any terms are missing, we need to add zeros for it. So in this case, I have x cubed, x squared, and then I have a term not there, and it jumps directly to 15. So what I'm going to do is I'm going to add a 0x there. So 6x cubed plus 11x plus 0x plus 15. And now we can actually do the division. So first of all, I'm going to think about, okay, I need to get rid of 6x cubed, but I have x squared as x squared minus 2 as the divisor. So x squared times what term give me 6x cubed? Well, x squared times 6x will give me 6x cubed, right? So I need the 6x. Where do I put that? I'm going to put that above the x term, which is the 0x. So I'm going to put 6x here. And now I can multiply 6x with x squared. So I get 6x cubed. 6x times -2, I get -12x. So I'm going to put it below the x term, so -12x. So you have to line up everything correctly to avoid mistakes. And then remember, I'm subtracting. So always subtract. So let's subtract. So 6x cubed minus 6x cubed, that's 0. And then I have 11x squared minus no x squared to subtract. So I get 11x squared minus 0. So just coming down directly. Then I have 0x, I added the 0 there. So 0x minus 12, let me highlight it. So here I have 0x positive minus -12x. So 0 minus a -12 is positive 12. So that's going to be positive 12x. And then I'm going to bring down the next term, which is 15. All right. So that's the first step. The second step is we try to get rid of the first term in this part, which is 11x squared. So I need to multiply x squared by something to give me 11x squared. So that means I'm going to multiply by 11. So plus 11. And if I take 11, now I'm going to multiply with x squared. So 11 times x squared, that's 11x squared. And then 11 times -2, that's going to be -22. So I'm going to put it below 15, -22. And again, just like before, I need to subtract this. So I got 11x squared minus 11x squared, that's 0. 12x minus no x, so that's a 12x. And the 15, positive 15 minus -22. So 15 minus -22, so that's 15 plus 22, that's plus 37. And that's the end of it, right? I'm not going to continue further because in the quotient here, I reach the constant term 11. I'm not going to continue further because if I add anything else, that's not going to be a polynomial expression. So this is my quotient. And this is my remainder. And the final answer I'm going to write is 6x cubed minus plus 11x squared plus 15 divided by, you can write like this, or you can put it as a fraction, divided by x squared minus 2. That's going to equal to 6x plus 11, the quotient, plus the remainder, which is 12x plus 37, but we have to put in the fraction notation, x squared minus 2. So this is my final answer. All right, any questions on this? All right, I'm looking through. All right, we can look at another division. It's called synthetic division. So synthetic division is kind of like a shortcut for long division. Instead of writing all the x cubed terms, so synthetic division, just use a coefficient. But it doesn't work for all examples. It only works if the divisor is a linear factor with the coefficient 1. So it works for divisor that is linear, that is a linear factor with coefficient 1. So what I meant by this is that, for example, if I take the previous example, this one, if I want to use synthetic division, I cannot do that because the divisor is x squared. It's not a linear factor like x. So it doesn't work that way. It doesn't work for that example. But it worked with the previous example. So the previous example, if you remember, I'm just going to write down the problem again. and I'm going to divide it using synthetic division. So the previous example I had was, let's see, I had 2x cubed minus 3x squared plus 4x plus 5 divided by x plus 2. So this works because x plus 2 is a linear factor, and the coefficient of x is 1. So it's okay to use this. And the setup for synthetic division is we only take the coefficients and then we're going to write them down. So we get 2, -3, 4, 5. So those are the coefficients of the dividend. And we're going to draw a vertical line looks like this and a horizontal line there. And then instead of writing x plus 2, instead of using +2, we actually going to find out the opposite number from a linear factor. So we don't use +2, we actually use the opposite number, which is -2 in the synthetic division. So we're going to put -2 here on the left side of this vertical line. So that's the setup. Now, I just want to point out that before I move on further, so the x here, sorry, not the x, the 2, not the -2, the first 2, that corresponding to the x cubed term, the -3 corresponding to x squared term, the 4 corresponding to x term, and the 5 is a constant term in the dividend, right? So what we do with synthetic division, you have to pay attention here, unless you know it already. The first step is we're going to bring down the 2. It doesn't change, just literally bring down the first coefficient 2. And then what we're going to do is we're going to take 2, the 2 that I got, this 2, and this -2, I'm going to multiply them together, and then it's going to go to this place, and the goes to the second number. So 2 times -2 is -4. So I'm going to put it there. So the first thing, we bring down the first number, 2, and then we're going to take that number, multiply by the number on the left, the -2, and I'm going to put it in the next place, below -3. So I'm going to erase those 2 circles. And then what I'm going to do is not subtracting. So here we have to add. So the -3 and the -4, we're going to add them. So always add in this synthetic division. It's not subtraction. In long division, we always subtract, but with synthetic division, we always add. So we're going to add -3 to -4. So we get -7. So after we add, we're going to bring the number down. So the sum going to go directly below the second column here. So now what I'm going to do is I'm going to take this -7 and I'm going to use a different color. So I'm going to take this -7 I just got, and again the -2 on the left side. I'm going to multiply them and to put the product into the next column below 4. So 2 times -2 times -7 is +14. So I'm going to put 14 here. Erase those 2. And again, just like the previous part, now we have to add them. So now we have 4 and the 14 in the same column. We have to add those 2 numbers. So plus them. So 4 plus 14, that's 18. This is the new number, 18. Right? We're almost done here. So that's 18. And then now I'm going to take the 18 and I'm going to multiply with the -2 on the left. It's always going to multiply by the number on the left. And then that's going to be -36. And then the -36, oops, let me move it out of the way. The -36 is going to go to this next column below 5. So that's a -36. And again, we're going to add the number that's already there with -36. So 5 plus -36 give me -31. Just like before, we're always going to add. So this is a synthetic division. It saves a lot of work, a lot of writing, at least. But you have to keep in mind that the process is not exactly like long division. Long division, we subtract in every step, right? but here we add in every step. And at the end, what we say is there's a last number. So we still have full numbers. If we begin with full numbers, we have full numbers, right? So the last number is always a remainder. And the 2, the first number 2 in this list, this 2 doesn't correspond to x cubed. It's actually corresponding to x squared term. And the -7 corresponding to x, the 18 corresponding to constant term. So basically the power of those terms reduced by 1 after synthetic division. So we can write down the quotient, which is 2x squared minus 7x plus 18. And then the divisor is going to be -31 divided by, sorry, not divisor, the remainder. It's going to be -31 divided by the divisor, x plus 2. So this will be my quotient and the divisor at the end. I'm sorry, the quotient and the remainder with the divisor at the end. So that's synthetic division. Any questions? I know it's not easy if you have not seen it before. The process could be really confusing. There's a lot of things to watch out for. I'm going to go through another example with you on synthetic division. All right, any questions before we move on to the next example? All right, the next example I have is we're going to take -9x to the 4th power plus 10x cubed plus 7x squared minus 8 divided by x minus 1. Now, as you can see, x minus 1 is a linear factor. The coefficient of x is 1, so it's okay to use synthetic division. Obviously, we can use long division, but I'm going to use synthetic division. So again, I'm going to write down the coefficients. We get -9, 10, 7. Now, be careful. So we have x to the 4th power, x cubed, x squared, that's 7. But it looks like we don't have an x term. So we're going to put an x there, but put a 0 below. So we have to fill in all the terms that's missing. And then we have a constant term, which is -8. So as you can see, I put a 0 below the x term. So this is my coefficient. Those are my coefficients. And I'm going to draw a vertical line and a horizontal line. And I need to decide what number goes on the left side of the vertical line. That will come from the divisor. So the divisor is x plus 1. So we're going to take the opposite of this number, which is going to be +1. That number goes on the left side of the vertical line. All right, so let me practice this process with you again. So the first thing we're going to do is we're going to bring down the first number, -9, so that directly goes down. So that gives me -9. And I take this -9, I'm going to multiply by 1. So take the 1 and the -9 multiply together and put it into the next column. So that's a -9. And now I need to add 10 and a -9. If I 10 plus -9. So remember we add here. So that's going to give me 10 minus 9, which is 1. And remember the next step is take this 1 and the 1 on the left. We're going to multiply them and put it into the next column, which is 1. Right? 1 times 1 is 1. Put it in there. And now I need to add again. So 7 plus 1 is 8. So I need to take this 8, multiply with the number 1 on the left, and put the new product into the next column. So 1 times 8 is 8. And now we have 0 plus 8 is 8. Good, well, it saves the trouble, right? And now we're going to take this 8 and this 1, we're going to multiply and put it into the next column. So 1 times 8 is 8. Oops, changing the color there. So 8 So now I'm going to add again. So in this case, the 8 and the -8 when I add, so I also add it here, but I just didn't write it. So -8 plus 8 is 0. Okay. So what that means is that's fine to have a 0 at the end. Is actually a good thing. So what that means is that this is 0 at the end. It's my remainder. So that means I don't have any remainder left. So I divide it perfectly. We take x minus 1, divide it perfectly into the polynomial. So because I begin with x to the 4th power, so in the divisor at the end when I write done, so those are the coefficients of the the quotient. So in the quotient, I don't begin with x to the 4th power. I begin with x cubed, x squared, x, and a constant. So I have at the end -9x cubed plus x squared plus 8x, and then plus 8. So this is my quotient. And like I said, the remainder is 0, so there's no need to write the remainder. Any questions? All right, so that's one thing I want to mention here because it's very important. That's the whole point of this, like synthetic division and long division. So for polynomial division, let's just say P of f of x divided by divisor is d of x, for example. If the remainder is 0, so we don't have any remaining, then both divisor and this is my notation for and quotient. So both the divisor and the quotient are factors of polynomial function or polynomial expression f of x. So what that really means is that so the f of x can be written as d of x, the divisor, times the quotient. Let's see q of x. So this is the divisor, quotient. If I just use parentheses, what that means is that f of x, whatever the expression is, could be written as this notation, 2 parentheses multiplied. So that's the case when we don't have any remainder. Any questions on this? And we're going to look at more examples on how to use the polynomial division to find the zeros or to find the x-intercepts of a polynomial function. So that will be the next tomorrow. So just, I guess the final takeaway from today's lecture is just remember that if the remainder equals 0, that's a good thing because you get the factors of the polynomial given, of the polynomial expression. That's a good thing to have always, because if we have any remainders, then what's the point of going through the trouble, right? Because the remainders, you can't really do much about it. All right, on that note, any questions at all from, I guess, about the quiz, which we're going to take in a minute, or just about lecture today? I'm not hearing any questions, so let's see. I need to set up a breakout room for one student, but before I do that, let's just talk about the quiz. Let's see, here's the quiz. I think you can still see my screen sharing. Good. All right, so let me just quickly show you where the quiz should be. It's not available yet, but it will be in a minute. So let's see, student view. So you should be able to access the quiz by going to pages. And then here you see quiz 1. So if you click on it, it should take you to the quiz once it's available. I think you can also go to modules. Do they have quizzes? Nope. Maybe when I publish it, it's going to be available somewhere here. You can find quizzes. Yeah, so pages, probably the place to go. Maybe modules. I just want to show you where you can find it. One thing about the quiz. Well, why don't I click on this for now? So if I go to quiz 1 in week 2, it says I don't have access. Okay, interesting. I'm going to leave student view. If it's published, you should see something like this. There's no calculator, textbook, notebook, online resources, or talking to someone else is allowed. So don't do any of this. Just do your best. It says write your solutions on a blank notebook, notebook paper, or blank printing paper, whatever paper, or graphing paper is fine. Just make sure that there's no like a lecture notes at top of the page, right? So if you use your notebook to take notes, just move to a next page, the new page, to start working on the quiz. And then you do not need to write down the problems. The quiz problems, just leave them, just label your solution, like number 1, the solution is this, number 2, write down the solution. Leave some space between number 1 and number 2. Make sure it's easy to tell the difference between solution to number 1 and solution to number 2. All right. You don't want me to spend a lot of time looking for your answers. All right. And if you usually write with iPad or tablet, that's totally fine to write down the solutions on those devices and to save it as a PDF at the end. But if you work on papers, just make sure that you scan all pages into a single PDF file. I don't want to have multiple pages attached when you submit your work. And also, I don't want to see pictures, because pictures are very difficult for me to grade on. PDF files are the best. All right, so make sure you submit your solution in the correct format to avoid any problems. All right, let's see. You do not need to stay on Zoom, and actually, just feel free to leave Zoom when you work on the quiz. And I should be around, but I'm going to mute myself and turn on my camera. So if you have any questions, feel free to come back to Zoom. Like I said, you do not need to stay here, and you do not need to keep your camera on. Like I said, just be responsible, right? Take your own quiz. There's no need to cheat or anything. I'm sure you wouldn't be cheating anyway. Just be honest. That's all. All right. Any questions about the quiz? Okay, like I said, the quiz is probably going to take about 20 to 25 minutes, but I'm going to give you, it's 7:58. So I would say do your quiz and then finish uploading them by 8:40. Is that a good time? It'll give you like 40 minutes in total to work on the quiz and to submit your solution. All right, I see a thumbs up from Luke. Excellent. So I'm going to make this available now. So can someone access the quiz and let me know if you can open it? All right, great. So go ahead, work on it. Like I said, you don't need to stay on Zoom. Feel free to leave. And Tim, let me set up a, let's see, Tim. Wait. Oh, I just stopped sharing. So let me create a